Introduction to the Inefficiency of Equilibria. This chapter presents motivation and definitions for quantifying the inefficiency of equilibria in non-cooperative games. We illustrate the basic concepts in 4 fundamental network models, which are studied in depth in the subsequent chapters. We also discuss how measures of the inefficiency of equilibria can guide mechanism and network design. In Inefficiency of Equilibria, the previous 2 parts of this book provided numerous examples demonstrating that the outcome of a rational behavior by self-interested players can be inferior to a centrally designed outcome. This part of the book is devoted to the question, by how much? To begin, recall the prisoner's dilemma, example 1.1. Both players suffer a cost of 4 in the unique natural equilibrium of this game, while both could incur a cost of 2 by coordinating. There are several ways to formalize the fact that the natural equilibrium in the prisoner's dilemma is inefficient. A qualitative observation is that the equilibrium is strictly paired to inefficient in the sense that there is another outcome in which all of the players achieve a smaller cost. This qualitative perspective is particularly appropriate in applications where the cost or payoff to a player is an abstract quantity that only expresses the player's preferences between different outcomes. However, payoffs and costs have concrete interpretations in many applications, such as money or the delay incurred in a network. We can proceed more quantitatively in such applications and posit a specific objective function defined on the outcomes of the game that numerically expresses the social good or social cost of an outcome. 2 prominent objective functions are the utilitarian and egalitarian functions, defined as the sum of the player's cost and the maximum player's cost, respectively. The natural equilibrium in the prisoner's dilemma does not minimize either of these objective functions. Introducing an objective function enables us to quantify the inefficiency of equilibria, and in particular to deem certain outcomes of a game optimal or approximately optimal. The primary goal of this part of the book is to understand when and in what senses game theoretical equilibria are guaranteed to approximately optimize natural objective functions. Such a guarantee implies that selfish behavior does not have severe consequences, and thus the benefit of imposing additional control over players' actions is relatively small. Guarantees of this sort are particularly useful in many computer science applications, especially those involving the internet, where implementing an optimal solution can be impossible or prohibitively expensive. In the remainder of this section, we discuss different measures that quantify the inefficiency of equilibria. In section 17.2, we illustrate these concepts and motivate chapters 18 to 21 via several examples in network games. Section 17.3 demonstrates how these same concepts provide a comparative framework for mechanism and network design. Section 17.4 concludes with bibliographic notes and suggestions for further reading. Measures of inefficiency. Several measures of the efficiency of the equilibrium of a game have been considered. All of these measures are defined roughly as the ratio between the objective function value of an equilibrium of the game and that of an optimal outcome. To specify such a measure precisely, we must answer the following basic modeling questions. 1. How are the payoff or costs of players expressed? 2. What objective functions do we use to compare different outcomes of the game? 3. What is our definition of approximately optimal? 4. What is our definition of an equilibrium? 5. When there are multiple equilibria, which one do we consider? We next discuss at a high level the most commonly studied answers to all of these questions. We give several examples in section 17.2. The answer to the first question will be some concrete payoff that players seek to maximize, such as money earned, or at a cost that players aim to minimize, such as network delay. Both cases arise naturally in the applications studied in this book. Second, we focus primarily on the utilitarian objective function, where the goal is to maximize the sum of players' payoffs or minimize the sum of players' costs. However, we also studied the egalitarian objective function in section 17.2.3 and chapter 20. We call an outcome of a game optimal if it optimizes the chosen objective function. For example, in a prisoner's dilemma, the coordinated outcome is optimal for both the utilitarian and egalitarian objective functions, while in principle the measures of the inefficiency below make sense for most objective functions. We can only expect the outcome of selfish behaviors to approximate an optimal outcome when the objective function is related to the player's objectives. Third, we quantify the extent to which a given outcome approximates an optimal one according to the ratio between the objective function values of the two outcomes. We consider only non-negative objective functions, so this ratio is always non-negative. By convention, we interpreted the ratio c/0 as 1 if c equals 0, and as a positive infinity if c is greater than 0. So this ratio is at least 1 for minimization objectives and at most 1 for maximization objectives. In either case, a value close to 1 indicates that a given outcome is approximately optimal. For example, in the prisoner's dilemma, the sum of the player's costs in the Nash equilibrium is 8. Since the minimum possible sum of costs is 4, the corresponding ratio for the equilibrium outcome is 2. As section 17.4 discusses, this use of a ratio is directly inspired by many similar notions of approximation that have been widely studied in theoretical computer science. While other notions of approximation are possible, almost all work on quantifying the inefficiency of equilibria has followed the approach taken here. Several equilibrium concepts have been studied in different applications. In this chapter, we confine our attention to Nash equilibria and their analogs in games, where the set of players or strategy is not finite. One particularly important issue not addressed in this chapter is the relationship between the inefficiency of equilibria and the ability of players to reach an equilibrium. In other words, a bound on the inefficiency of the equilibria of a game is much more compelling if we expect players to learn or converge to one of these equilibria. In many of the games discussed in this part of the book, relatively weak assumptions imply that local uncoordinated optimization by players leads to an equilibrium outcome in a reasonable amount of time. See sections 4.7 and 29.3. Some important classes of network games, however, do not admit such convergence results. This fact motivated researchers to define novel notions of equilibrium outcomes, which include all Nash equilibria, but also allow players to wander among a set of unstable outcomes. In some applications, all such equilibria, and not just the Nash equilibria, are guaranteed to be approximately optimal. Chapter 19 briefly discusses some results of this type. See section 17.4 for further details. Finally, given a choice of an objective function and an equilibrium concept, a game may have different equilibria with different objective function values. Recall, for example, the coordination games of section 1.1.3. In such games, it is not clear which equilibrium should be compared to an optimal outcome. Section 17.1.3 discusses the two most popular approaches: the price of anarchy and the price of stability. The price of anarchy, the most popular measure of the inefficiency of equilibria, resolves the issue of multiple equilibria by adopting a worst-case approach. Precisely, the price of anarchy of a game is defined as the ratio between the worst objective function value of an equilibrium of the game and that of an optimal outcome. Note that the price of anarchy of a game is defined with respect to a choice of objective function and a choice of equilibrium concept. For example, as shown in section 17.2.3 below, the price of anarchy of a game is generally different for different choices of an objective function. We are interested in identifying games in which the price of anarchy is close to 1. In these games, all equilibria are good approximations of an optimal outcome. We view selfish behavior as benign in such games. Put differently, the benefit provided by possibly costly or infeasible dictatorial control over the player's actions is reasonably small. A game with multiple equilibria has a large price of anarchy even if only one of its equilibria is highly inefficient. The price of stability is a measure of efficiency designed to differentiate between games in which all equilibria are inefficient and those in which some equilibrium is inefficient. Formally, the price of stability of a game is the ratio between the best objective function value of one of its equilibria and that of an optimal outcome. Of course, in a game with a unique equilibrium, its price of anarchy and price of stability are identical. For a game with multiple equilibria, its price of stability is at least as close to 1 as its price of anarchy, and it can be much closer. See example 17.2 below. A bound on the price of stability which ensures only that one equilibrium is approximately optimal provides a significantly weaker guarantee than a bound on the price of anarchy. Nevertheless, there are two reasons to study the price of stability. First, in some applications, the non-trivial bound is possible only for the price of stability. See section 17.2.2. Second, the price of stability has a natural interpretation in many network games. If we envision the outcome as being initially decided by a central authority for subsequent use by selfish players, then the best equilibrium is an obvious solution to propose. Indeed, in many networking applications, it is not the case that agents are completely independent. Rather, they interact with an underlying protocol that essentially propose a collective solution to all participants who can either accept it or defect from it. The price of stability measures the benefit of such protocols. Because of this interpretation, the price of stability is typically studied only for the equilibrium concepts that involve no randomization, such as a pure strategy-Nash equilibrium. For example, since a mixed strategy-Nash equilibrium might randomize only over outcomes that are not pure strategy-Nash equilibria, it is not clear how to interpret it as a single proposed outcome for future use by selfish players. The price of stability thus quantifies the necessary degradation in solution quality caused by imposing the game theoretical constraint of stability. The goal of seeking a good equilibrium is reminiscent of the general motives of mechanism design. Part 2. Designing a game outcome that approximately optimizes a social objective function and is also consistent with self-interested behavior. In this book, we will only quantify the inefficiency of the worst or the best equilibrium of a game. A third interesting approach is to analyze a typical equilibrium. Such average case analyses are notoriously difficult to define in a meaningful and analytically tractable way. However, and this approach has not yet been used successfully to study the inefficiency of equilibria.